Okay, welcome everyone to the robust optimization webinar of this week. So I'm very happy to introduce Emilio Carrizosa. He's a full professor at the University of Seville. He does research in mathematical optimization, OR, data science, and many other fields. He's the author of more than 115 articles in all types of leading journals in OR. Also, he's president of the Math In, which is the Spanish network for industrial mathematics, and also editor-in-chief of Top. And I'm very happy to have you here, Emilio, so please go ahead.
Thank you very much. Thank you, Yanis, for your words. Thank you, Yanis and Amadresa, for inviting me to participate in this webinar. Let's see if I am able to share my slides. I hope so. Okay, can you see my slides?
Yes, looks good.
Okay, so what I'm going to present today is, in fact, a superposition of a couple of works I am doing with three colleagues, Renato De Leone and Marica Magagnini from Università di Camerino in Italy, and a PhD student of mine, Antonio Navas, in the Institute of Mathematics of the University of Seville. The title, as you can see, is Making Counterfactual Explanations Robust. In fact, as Yanis has said, I am working I'm working in optimization, but I am interested in the applications to machine learning, and in particular to explainable machine learning, in which I think that in order to make machine learning procedures interpretable or explainable, optimization is a fantastic tool. So I'm taking this opportunity to work on bridging somehow mathematical optimization and machine learning or explainable machine learning. And one of the tools in explainable machine learning when you're looking for post-hoc explanations for a given prediction model is what is called counterfactual explanations that I'm going to revise in a second. And of course, since I am speaking in a robust optimization webinar, the term robustness should appear in one way or another, and it is going to appear because many of the colleagues are already doing. In fact, you may have several types of uncertainty in a machine model, even in some cases. Before going to my talk, in fact, just to show is that, well, this one is a fantastic webinar. But if you have even more time, I invite you to attend to the Monday sessions research. And in fact, you can follow the link, or you can Google Euroline Seminar Series, and you will find us where we are. These talks are just bridging, as I'm trying to do right now, OR and machine learning. So going back to my talk, or starting with my talk, I would need to say that if we go to biology principles, by the way, wrong biology principles, but Jean-Baptiste Lamarck, Lamarck said that the power of life tends continually to build organization, and this increases complexity. And this increase of complexity, we have seen it in many places. We have seen it, for example, in art, and you see old art and recently, a little bit more recent art, I would say. And the same way that we have seen this in art, we have seen this in data analysis. And up to the 20th century, I would say that when one was doing some sort of data analysis, roughly we had some sort of regression governed by linear regression which perhaps was not that accurate, but it had the advantage that it was very interpretable because, of course, you can give an interpretation to the different coefficients in the linear model and relate, for example, what would happen if I increase in 1 unit a given variable in terms of the output obtained. This was, I would say, until 20th century, but if we take the last part of 20th century and in fact 21st century, I would say that we have an explanation blackout. Everything has become much more complex, as in Lamarck statement for biology, but at the same time more accurate, but also less explainable. And perhaps the guilty of that at the same time that the promoter of this revolutionary change has been neural networks and everything around. So nowadays, we are very happy with the accurate black box systems in machine learning, but at the same time, we are quite concerned about the lack of explainability of many of these procedures, and there's a trend, also a scientific trend, uh, to find a balance between accuracy and interpretation. And in fact, this may be even a societal and a political trend, even also to give to citizens. And in academia, I found many different approaches, different strategies to address explainability. Some of them may be using simple models, and I make, for example, linear regression models, as discussed in some slides, or at the time classification regression for other simple procedures that easily understood, or we may accept that we are going to have complex models, but locally we are going to obtain some simple approximations as a line example, or we want to do like, okay, we're going to identify which most relevant features by measuring the important attributes with things like, for example. And this is
Emilio,
the
sorry
topic I am
to
going to develop a
interrupt.
bit right now.
Okay, I think he disconnected.
I think you spooked him.
Yeah. Hi, Emilio.
Again,
Yeah, your internet connection was very bad. Bit of
have I been
delay.
lost?
Yeah, and I think you got lost at some point.
Do you know what point so that I can recover? I can go back.
Yeah, this slide was the last I think we saw.
This slide was the last one. This was the last I
Yeah,
presented. So you did
yeah,
not
yeah.
meet mass. Okay,
No, we
I can
could hear you,
recap.
but you were very delayed. So
Okay, so should I speak slower, perhaps?
no, it's everything fine. It's just when your internet connection is going down, then we cannot properly listen, but let's try. I mean, there's no way around it, I guess.
Okay. So different tools for making processes explainable, either the process or the output. And in particular for the output, we have counterfactual explanations, which is what I am going to discuss right now. No, this was not what I was going to do. I don't know why I have gone to the end. You're seeing I'm having lots of slides. Lots of slides. Okay, so the basic thing of counterfactual explanations for those you don't know. Imagine you have a prediction model. For example, for someone applying for a loan, there's in the bank, there is a system, maybe a complex black box system governed by a deep neural network, something like that. I don't care. The thing is that this prediction model is already trained. I don't need to do anything on the training of this machine learning prediction model because this is already trained. But now I receive a record. For example, the record is this lady with these two features. She applies for a loan and the loan is rejected. And the person asks why. The point is that, okay, if this is rejected, what I would like to do is to say, okay, your loan has been denied because your salary was 25 and you had four accounts. But however, if instead of 25, you had 30K in salary and you had two accounts instead of four, in this case, the same machine learning model would have accepted your proposal, your request of a loan. So the point is, how should I minimally perturb my attributes in such a way that I can obtain the loan? So this is the problem in this example. And if we go to something more general, the thing is that what we are going to have is a prediction model that goes from the set of features to the real numbers. And when I'm talking about a prediction model, I may, for example, assume, and I am assuming it in a couple of slides, that what I have is a classification problem, and P represents the probability of belonging to the positive class, which that I am going to assume that it is the good class. So the class of good payers or healthy people, whatever. So I'm considering, for example, that I have a binary classification problem and P represents the probability of being in the positive class. But I am not restricted, although most of the literature in counterfactual analysis is restricted to classification models. We can have any type of regression model in which, for simplicity, we are considering that the output is desirable, like in the first case, which was the probability of being in the good class. If I have a regression model, I consider that this output is desirable, so the higher the better. And I'm having a record. The record was, for example, here, the lady with these two features, 25K and 4. And what I want to do is to address, for example, the problem of, okay, I am my features in x0 and I want of perturbing my features from x0 to x in such a way that the prediction, whatever it is, for example, the probability of positive in a classification model is above a given threshold value. Please take into account, or if we are allowed to vary it, when we vary the right-hand side tau, in fact, what we are doing when solving the problem for the different values of tau, what we are doing is describing the weakly efficient, or the Pareto, in some cases, frontier for this bi-objective problem of minimizing the cost of perturbing the features and maximizing the prediction under the constraints given. I am not going into the details because you have a lot of recent literature on that, but of course there's a discussion on what type of constraints you should add here in the problem. Depending on them, you're going to have a discrete or perhaps a continuous optimization problem. How you are going to model the cost. Roughly, we are going to consider that the cost has, the perturbation cost has two components. One is the measure of distances, and the other one may be related to the complexity, because I want to perhaps perturb just a few features, and at the same time, the dissimilarity part is related with a norm, or even if I am not happy with symmetric dissimilarities, because, for example, for me, it would be much easier to have a job with a lower salary than with a higher, with a job with a higher salary, since perturbations may not be equally costly. For example, then perhaps instead of using norms, we should use Minkowski functionals, gauges, but in fact, for simplicity, in what follows, I am going to take most of the time that I am taking just Euclidean distance, but take into account that most of the things I'm going to mention can be extended to other norms and also to Minkowski functionals, to gauges which are asymmetric. Okay, this problem is not new at all, and many people have been working here. You have a couple of, say, basic references, and in terms of optimization approaches, different techniques have been used depending especially on the nature of the ingredients you have here, about the cost, about the prediction model, about the structure of the feasible region X we're having here. So depending on these ingredients we can find in the literature different approaches, different numerical approaches to pursue either solving the problem for a threshold value of the parameter or to describe the Pareto front in this bioobjective problem that I have analyzed. Well, in fact, with this seeing this optimization problem this way, it seems we are in paradise in the sense that we are going to give solving this optimization problem or this parametric optimization problem, we are going to give having the loan, but you will receive the loan. In practice, we are not that in paradise. We are not that much in paradise. Perhaps we are closer to hell because we may have several uncertainties in this process. In the sense that, for example, it may be the case that the point at which we want from which we want to calculate the counterfactual is affected by some errors. These errors may be noise in the measurement, but also they may be due to an aggregation of information. And in fact, perhaps the input x0, so the coordinates of the record we are interested in calculating a counterfactual for, they may be partially wrong. So there may be some uncertainty about this. At the same time, once we have decided and we said before, okay, you should have a salary of this and you should have this number of bank accounts, perhaps this is a proposal, but perhaps this proposal is not really implemented. The person is not able to implement exactly this and is implementing something perhaps close, but not exactly the same. So we may have also uncertainty or noise or errors in the implementation of the counterfactual. And finally, we are assuming that we have a ground truth, which is a P, the prediction model. And in some cases, that's a way. For example, if we are talking about a black box model, a black box prediction model used by a bank, what we want to know is what should I change in such a way that this model, either correct or wrong, is saying, yeah, you deserve the loan. But in some other cases, it's not like this. If we are talking, for example, about being healthy, and we have some machine learning procedure that labels us as healthy or not, in fact, I don't want to change my habits in such a way that I pass the test of the machine learning tool. I want to be healthy, which is not the same. So perhaps the prediction model I am using to predict how healthy I am is just an approximation and perhaps affected by a lot of noise of the ground truth model. So in some cases, I am just interested in the ground truth model. In some of the cases, I am not. But in any case, this is another source of uncertainty I may find. Okay, this has already practical applications of this tool of counterfactual explanation, and many people have already been addressing these issues and considering, for example, the model of devils and things like that. Okay, so after this more or less presenting where we are, or where now I'm going to start discussing where I want to be. And as I said, what I'm presenting is a mixture of a couple of papers, in fact, ongoing work. And I'm going to start with an ongoing research with my Italian colleagues, Renato De Leone and Marica Magagnini, in which we are going to talk about, and I'm going to talk now about this stuff of counterfactual analysis, counterfactual explanations, in the case in which I have some noise or some uncertainty, I would say, but the prediction model is already fixed and it has a very specific structure, which is nearest neighbor. If we go to the traditional nearest neighbor, K nearest neighbor, so we have the problem you have at the top. You want to minimize the cost of the perturbation, assuming that the prediction is going to be above a given threshold value within a given feasible region. You have your data set. And as I said before, we are going to assume without loss of generality that the positive class, the class 1 is the desired class. And if we are talking about nearest neighbor as a classifier, then what I need is simply a metric space. I calculate the k as smallest values in the distances from the point X to the points in my data set. I define the neighborhood as the index set of the instances which are below this value. And these are the k. In fact, what I want to do is to have the k nearest neighbors be more than exactly k. So the set nk is going to have cardinality at least k, but perhaps in case of ties, I'm going to have a little bit more. So in this case, with this definition, the P, the prediction model in this binary classification context, will be the fraction of the individuals or the records in the K neighborhood that has label equal to 1. And usually, if I need to have not the fraction, which can be understood as a probability, if I want to have a 0-1 rule, then I'm going to take, for example, if I am above 0.5, then I'm going to say that I am in the positive class. But in principle, I can say that P is the fraction of individuals in the neighborhood which are in the positive class. So this problem, the problem of building counterfactual analysis, so solving the optimization problem you have at the top, for the case of nearest neighbor classifier has already been addressed by Claudio Contardo and co-authors, and also Marica Magagnini and co-authors in recent papers. And what I'm going to do now is to say, okay, let's introduce uncertainty. And one possibility for modeling uncertainty in the data is replacing the features, the coordinates of the individuals by sets. So I'm going to assume from now on that my training data set consists of pairs. These pairs have the second component is the label 1 or 0, and the first one, instead of being points in j-dimensional space, are going to be sets. In particular, we are going to assume that they are, as in these two examples, you have convex compact sets. I know that this is a very strong assumption, but it is quite useful to make the problem tractable. And in fact, you can consider very interesting cases, such as considering hyperrectangles or considering spheres. And both are quite reasonable, because you may say that you have a nominal value, and then you have the uncertainty just given an uncertainty in each coordinate in the case of rectangles. So you may have a ball around this point with a given uncertainty budget R, like this. So we are going to assume, for example, that we have rectangles or spheres, but in principle, the thing is that I need to have convex compact sets there to model the data. And in this case, the blue data represent individuals in the bad class, in the class 0, and the red ones, individuals in the good class, in class 1. At the same time, since I am assuming at the same time that I may have uncertainty in the implementation, I am not going to say, okay, the point X is the point I want to reach, but perhaps I don't reach X, but instead I reach a point of the form X plus S, where S is, say, the noise or the error in my implementation. And the S is going to vary in a given set S, capital S, that I am going to assume again that it is a convex and compact set with a 0 there inside. So this may be the context I have, and in this case, in the end, my counterfactual set may be in both cases the yellow region in which I am pointing at X, but then I don't know exactly where I am going to, what is the final point I'm going to reach. I'm going to reach some point in the region X plus S. Okay, so this is what I am going to do. And yeah, the thing is that I was assuming that I had a metric, and I need to extend this metric from points to a metric for sets. And of course, there are many possibilities already studied in the literature. You may consider the infimal distance. You can consider the maximal distance. You can consider the average distance for some probability distributions. You can consider the second moment of the distances. These are just some examples. But the original metric D was given by a norm. Then, in fact, we can rewrite in these expressions we have above, we can rewrite this delta as a function only of X and on the Minkowski difference between U and S. And due to the compactness and convexity assumptions of U and S, the set U minus S is a convex set, and also the distance from a point X in the space to U minus S, as soon as the delta is induced by a norm, is going to be a convex function. So this means that we can use identically, I would say, the thing that we have an error for the implementation, or uncertainty for the implementation, uncertainty for the input for the data, or we may assume that we have, for example, zero error in the implementation, but for the input we have larger sets because instead of U we're going to have the Minkowski difference U minus S. Okay, the good thing is that for these expressions, if our delta is coming from the Euclidean distance, and our sets are, as I said before, either rectangles or spheres, then we may make some calculations here, and in particular, we may have analytical and simple expressions for example, the D0. D0 was the minimum distance, and D1, which was the maximum distance. For the average distance, it is a bit more complicated, actually much more complicated. But if instead of this we take the second moment, then again we may have we have a closed formula, which in fact can be computed analytically very easily in case we are assuming that within the rectangle or within the sphere we are having a uniform distribution. Okay, so let's do in a moment our first attempt, and I am making a spoiler because I am announcing that this is a failed attempt, which is, okay, now we have a distance for sets. Let's extend the idea of the KNN classification model, and then build the counterfactual explanations for this. If we do this, then we can, okay, as we said before, now we calculate the k smallest values in the distances. We define, and now we consider that the neighborhood is consists of those points which are the k closest ones. But in case of ties, we need to be more subtle and consider the neighborhood of those which are below this threshold value Rk. And again, extending what we had before, we could say that the classification model yields in this case the fraction of rectangles or spheres or something like that, labeled as 1, out of those rectangles or spheres which were in the neighborhood. Okay, we may have something like this, and in this case we are having for both the blue rectangles, which are those in the class 0, in the bad class, and those rectangles which are in the red class, which is the good class. If we are taking, for example, as written here, in both cases, for both classes, the distance 0, so it was the minimal distance. Then, for example, if our counterfactual set was were this one, the distance to each of the records I have these rectangles would be the minimum distance. So this would be, in this case, this would be the length of the segment. With respect to U4, this would be 1.25, which is the length of the smallest distance separating x plus s and U4, etc., etc. And if we are considering, for example, the neighborhood with k equal to 3, it turns out, if you see these numbers, that the 3 closest points in terms of the d0 distance would be the 3 red rectangles. The red were the good ones. So this means that in this case, our prediction for this counterfactual in yellow would be that this counterfactual in yellow has a prediction of 7%, because the 3 out of 3 rectangles considered in the neighborhood, the 3 of them are in red. But this may be very over-optimistic, because since we are assuming some uncertainty on, for example, U4, imagine that instead of having a realization of U4, which is really close to the yellow square, we might have had a point which is in the antipodes, and in this case, perhaps this would not be perhaps so close as we are considering here. So this means that okay, it is true. Formally, mathematically speaking, we have already given a model for the distances, but we are not properly addressing uncertainty, because we are treating in the same way the good points and the bad points, so the good rectangles and the bad rectangles. And perhaps it would be much more conservative if I want to be in the safe side to say, okay, for the red ones, which are the good rectangles, if I am going to, I want to see them as if they were farther from me than if they were in blue, in such a way that I tend to incorporate in the neighborhood more blue rectangles, just in case. So with this idea, we have the second attempt to define a KNN for classification with sets. And the idea could be to say, okay, let's introduce what we call a label-sensitive distance, in which we are considering the distance from a set, not to a set, but to a pair of the set and the label. And we are going to assume that we have higher distances if the element u to which we want to reach is in the positive class. So that if it is negative, we are using the worst case, I would say, and if we are in the positive class, we are using we are assuming that the point we are going to reach is the farthest one instead of the closest one. So typical examples may be, for example, to consider that, as I said before, if we are for a rectangle or a set U, which is in class 1, we are going to consider the distance as the farthest distance. And if the U is in the class 0, then we are going to consider the closest distance instead. So that we are considering the worst case, in which red rectangles are close, near, and blue rectangles, even with the same coordinates, are considered to be far. This is not the only case, of course. Even playing just with those that we have considered earlier, we may consider the second moment for the class 1, and the 0 distance or the infimal distance for the class 0, for example. And now, assuming we have this, we define same way as before our prediction as the fraction of sets in the class 1, but out of the k closest, out of those in the neighborhood. But in the neighborhood, points which are in the positive class are penalized, so that I tend not to include them in the neighborhood. Let's see this with an example. The first one was the label insensitive, the label insensitive we were seeing before. And just now, considering if we go to the extreme, to the picture in the right with the same coordinates, observe that now we are measuring for the red ones, so the positive ones, we are measuring distances according to the D1, so the maximum distance. So we are using a worst case analysis, and we are assuming that we need to reach the farthest point. However, for the blue ones, those in class 0, we are being conservative, and we are assuming that we are going to obtain the closest point instead of the farthest point. So in this case, you see there the calculations of all the distances in this case. And now it turns out that, for example, if we are again using the 3 in n, so 3 nearest neighbor procedure, the three neighborhood in this case for this yellow set would consist of not 3 red rectangles as before, but in fact 1 red rectangle and 2 blue rectangles, which means that instead of being over optimistic and measuring and having a classifier giving a prediction of 1 as we had before, now we would have a prediction of 1/3 in the for the very same yellow rectangle. And well, the intermediate case is something in between, I would say. Okay, how can we solve this problem in this particular case? Well, in fact, if we want to solve the problem, we want to find an x, so the point at which we are going to point at, although we know that perhaps it is not reached, and we obtain something around this point. We want that the prediction, the fraction of sets in the neighborhood which have the label 1 should be above the given threshold value tau, and we want to minimize the distance, but now the label sensitive distance between the yellow set x plus s and the record, the set u at which we are giving a label 1 in this case. So this is the optimization problem we want to solve. This is quite general, but in order to convert this into a mathematical optimization, a more or less tractable mathematical optimization problem, the thing is that, well, unfortunately, we don't know, as I said before, how many individuals we have in our neighborhood. We may have, we're going to have at least k, but we may have more. So the thing is that we may consider in the formulation that we may define associated with each record binary variables v and w, the w representing whether a given record, a given set is in the neighborhood, and the v is going to take the value 1, not only if it is in the neighborhood, but it is in the neighborhood at the distance less than the distance, the rk that I said before, the distance indicating the boundary of the neighborhood. So what we do is we consider the rk as a decision variable, although it is going to be determined. And we impose that in our neighborhood, we should have at least k individuals, but with strictly smaller distances, we should have strictly less than k individuals. The third inequality in the constraints is, in fact, a rewriting of the constraint, the constraint written above. And the remaining inequalities with the big M's are just clean, but perhaps not for illustrative purposes, expressions of what I have said, that W counts whether a point is in the neighborhood, and V counts whether a point or set is not only in the neighborhood, but also at a distance strictly smaller than the radius R. Unfortunately, I have strict inequalities R in some of the constraints. This is not that nice, and I'm sorry to say that, but I need to do the dirty job of adding a small positive epsilon here, which is going to make the problem even less stable because now I'm going to have an epsilon and a big M at the same time, for example, but this is what I have. So this might be formally a formulation for the problem you have in the top of the screen for calculating this counterfactual set. This is quite general, but fortunately, as I said before, these distances are tractable in case my sets U are either rectangles or spheres, and my D, the functions I am taking are either the infimum distance, the infimal distance, the supremum distance, or the second moment distances. Before going this, here you have, and these are very bad news, we have for the same data set, a toy example in dimension 2. We have different choices of the distances, different choices of the parameter k. So this is 3 nearest neighbor, 5 near neighbors, 7 near neighbors. And what you see is that in the counterfactual analysis obtained in each of the cases is different, which is not nice. This means that there are some instability in the modeling issues. So this means that you need to have a clear idea of how you are choosing these parameters, the k, and also the way you're measuring distances. But at least this toy example can be solved to optimality as we are doing here. The thing is, when you go to this case, as I said, you can you can write for these particular cases a mention of distances and sets, rectangles, spheres. You're going to have, in fact, you can rewrite the problem as a quadratic optimization problem, but it's not quadratic convex. So you have non-convexities, many reverse convex constraints, and this means that you need to solve the problem with some heuristics. And to have it scalable and going beyond these 2D toy example problem. And in order to do that, we have developed some sort of VNS, which is VND, because we have a descent, and we call it feature type adaptive VNS or VND, because what we are doing is the perturbation, the shaking in this case, is going to be dependent on the type of variable we are having. If we have a feature which is continuous, then the VNS is going to make a Gaussian perturbation, as we do in Gaussian VNS. If we have a binary variable or categorical variable, we are going to make a shift with increasing probability when we increase the neighborhood, not mix with these neighborhoods in the NN, is the neighborhood of the VNS. And also we perform some local searches, and the idea of the local search is that we are going to perform some local search that is not going to perturb that much. So we're going to reduce the search to a region in which we are expecting to have the same neighbors. And in this case, instead of considering the full data set, which is including a lot of quadratic non-convex constraints, we are going to control the number of points we are going to add. So we have tested in this case for the toy example, for example, how the gap of using the VNS with respect to the exact solution for this toy example that we were able to solve. And you can see that indeed, if the time goes by, then you find that we are obtaining the optimal solution. But yeah, since we are perturbing, we are visiting the optimal and perhaps the pessimal solution as well. But what you see is that at least for this example, in which it is the only one that we can test for the moment, you can see that the heuristic is not performing that bad, especially if you give some time to do it. Well, some other examples in which, since your data may not be given by rectangles or spheres, but you're artificially building these uncertainty sets. Here we're considering a standard data set, which is the Boston housing data set. And in this case, we see here for different levels of uncertainty. So we're building rectangles with higher and higher width, or higher and higher lengths of its sides. and we see what happens. And what happens, of course, is that the perturbations you need to attain the same level of prediction is higher. Very quick, because as always, um, I take too much time in the in the first slides. Very fast. I'm going to say a few words about another topic, which is something that I am doing with Antonio Navas in Seville, which is talking about robust counterfactual explanations with GLMs. GLMs is an extension of linear models, including, for example, because in fact what you have is a link function, and what you're assuming is that your prediction is gonna G of your prediction is gonna be a linear model, where G is a strictly increasing function. So your prediction is gonna be a strictly increasing function of a linear function. That's it. And again, taking cases as logistic regression, as Poisson regression, for example, if you have a counting process, the nice thing is that you retain the explainability of the coefficient. So perhaps this is not that accurate in some cases, but you should always balance accuracy with explainability, and definitely GLMs are really explainable. But the thing is that, okay, if you have your GLM and something, you have then that G of your prediction is a linear model, you want to do again the counterfactual by solving the bi-objective problem, or by finding the bi-objective, the efficient solutions for this bi-objective problem. But of course, this is with the data set I have. With this data set I have, I would have these results. But if I perturb my data set, so if I assume that I have some uncertainty in the input, then the beta I am obtaining, so the classifier itself of the prediction model itself, is of course changing. And we could consider some perturbation, say, using a Wasserstein distance, and saying that the distribution of my records is going to be at the Wasserstein distance smaller than whatever, than from the uniform distribution in this discrete data set, for example. But perhaps I don't want to destroy correlations. I don't want to destroy the structure of the data. For example, if I have 0, 1 variables, I want to remain being in 0, 1, for example. And instead of this, what we could do is to consider, okay, the perturbations I am allowing are not in the coordinates, but in the frequencies. The points that I have observed are presented. So of course, if I change the frequencies, I am changing the beta, so I'm changing the prediction model, and then I'm going to change the result. So I may wonder, trying to be robust, that I can consider the bi-objective problem of minimizing the cost and maximizing the prediction in the worst case. And in the worst case is when the beta varies in a given set. And instead of taking a set, a ball, that it is a possibility, a geometrically very nice and very useful to make the problem tractable, but in the ball of the beta, of the nominal beta that I have obtained by, for example, maximum likelihood in this model, in this set, perhaps in this ball I have some betas that are not clearly that would not be obtained as maximum likelihood estimates. So instead of this, what we are suggesting is to say, okay, this is a problem I want to solve, and in any case, for any variation of the betas I have, this is the problem I need to solve. And if I write this as a max mean, the function that for each x, if I take into account the objective, the function that for each x gives me the optimal value of the inner problem. Of course, this is a concave function for which subvariance can be obtained by solving the inner problem I am considering. And of course, I can use cutting planes. So as I said, how am I going to choose B, the set in which I allow beta vary? No, I'm not going to take a ball. I'm going to take the maximum likelihood estimates when the distribution is at a certain distance of the empirical distribution. So doing this and taking as distance between the distributions, for example, the KL divergence, I can then define if capital L defines the log likelihood, then B is the set of betas that are maximum likelihood estimates for some distribution of the data, which is close to the empirical distribution I have observed. So my uncertainty budget is now given by the KL distance between the empirical distribution of my data and any distribution on the very same support. Okay, in order to have this well defined, I need to add some properties and so on. But the thing is that, okay, if you want to solve to see the details, we have the proofs are already online in Eager. You can see the details, but the thing that is that under the assumptions of log concavity, etc., of the log likelihood, then we can replace the constraint by a nonlinear, non-convex constraint because it is equal to 0. And well, in fact, the inner problem we need to solve is a problem which is going to be nonlinear, assuming we are able to solve this problem to optimality for a given x, then we can use a cutting plane procedure. Otherwise, if we are simply finding a stationarity point each time we solve this, then we don't have a guarantee of solving the problem to optimality, but at least we may have a heuristic and taking into account that, in fact, as I said before, we are only allowing the betas that have this this property of being maximum likelihood estimates. So some examples, you can go to the details to the paper, which is already online in Eager. As you can imagine, of course, when we allow a higher distance, then we obtain a higher likelihood or log likelihood in our case. And here you have the representation for different data sets of different records. So the record that is very in the bottom because it is in the percentile 10 in the predictions in the data set and so on and so forth. And in 3 minutes, I hope, I want to give to you one idea which that we are exploring. I am exploring with Antonio Navas, also in Seville, which is building counterfactual explanations with statistical warranties. The idea is a little bit different. So the thing is that, as I said before, in some cases I have a ground truth. For example, the prediction of being healthy, but and this is a parametric problem with an unknown parametric beta, and I am going to estimate the beta, maybe the estimate of the weights of a neural network that I am assuming that is the ground truth. And the thing is that since I have the data, what I have is an estimate of the ground truth beta. And then what I have is an estimate of the prediction, an approximation of the prediction of the real prediction model. And the thing is that I would like to find counterfactuals for the ground truth, but instead I'm having the counterfactuals for the approximate one. And it may be the case, and here you have the case in which the counterfactual I am proposing, which is the blue point, is not really a counterfactual because the ground truth region would be the region defined by the red line and not by the blue line. Of course, if the sample sizes are big enough, we are expecting that these two sets are not that different, so that perhaps the tau is almost the constraint is almost reached. But nevertheless, we are not sure about how far we are. I mean, if our sample size is large enough. And what we propose to do is to say, okay, suppose we are able to have a statistical hypothesis in which we check whether in the ground truth we are strictly below or we are above the threshold. So we have our data set. With our data set, we may build a statistical test for this hypothesis testing, and we may define the region of records or the points for which the null hypothesis rejected. So the set of points for which we have strong reasons to believe that in the ground truth model, which is something that we haven't seen, in fact, we are above the threshold value tau. And we can add this as a constraint. we can add this as a constraint. So we want to minimize the cost. We want to have the probability above tau, and we want to be in the region of rejection of the null hypothesis. The nice thing is that if we are in a generalized linear model as before, asymptotically, and under a few regularity assumptions, the beta estimate is going to be asymptotically normal, and in fact, we can analytically derive the rejection region, which is represented there, where z is the quantile of the normal distribution, and I is the Fisher information matrix. And the thing is that, in fact, what we have is that the constraint we are adding is a second order constraint. So it becomes linear in the limit case in which we are putting alpha in the limit of 0.5, in which we are simply recovering what we had before. Here you have an example that we have checked about the cost increase when we are having very strict confidence in the test. So if we want to be sure that we are not only passing the test, but that we would pass the test in the ground truth model. And if you want to know about the times, we have checked in a few, quite small data sets, but you can see that we can solve two optimality problems for GLMs because they are for logistic Poisson regression for these cases, a linear regression, of course. For these cases, the optimization problem we need to solve is a convex optimization problem. So this is the end. And just to summarize, we have proposed new strategies to incorporate uncertainty in counterfactual explanations. It's very important that depending on the type of uncertainty, but also depending on the prediction model we have, we are going to have different properties. And in particular, if we go to GLMs may not be that accurate if we compare with things like, I don't know, deep neural networks. But on the other hand, they are very easy to interpret. And of course, the optimization problems to be solved are quite easy, much easier. And then finally, if you want to do something more scalable, and in particular, if you have binary variables and so on, then perhaps you need to go to heuristics, perhaps more sophisticated than the VNS we have been proposing. So this is the end. I thank you all for your attention. Thanks to Yanis and Amadresa again for inviting me. And here you have the QR for my ResearchGate site with links to the different publications we have in the team on the topic. And just in case you want to contact professionally, in addition to my email address here, you have my LinkedIn profile. Thank you very much.